So I was doing some thinking and I thought, the last video that I just recorded, I wonder if I got, I don't know, a bit too deep in the math. I hope I didn't. Because, I was, like I said, I was doing some thinking and I don't want this series of videos that I'm putting together to be, positioned as like electrical engineering educational videos because I don't want to do that. I mean, for a number of reasons. I mean, there's plenty of stuff out there. There's lots of content out there that teaches, teaches all of us, myself included. I learned a lot from watching videos on YouTube and reading articles of how transistors work and how MOSFETs work, and the simple Ohm's law and current design and all that sort of stuff. And the base of electronics. There's so much content out there. I don't want to compete with it. Secondly, I don't. I went through school as an engineer, so I guess I graduated as an engineer. I never did anything. I didn't do an advanced degree in engineer, so I didn't get my master's or anything like that. And I certainly didn't graduate at the top of my class. So I'm not one of those elite, electronics people. Absolutely not. I think I know enough to get by. But again, I wanted to use this opportunity to share it with you, but also learn from you too. And so I don't want to pretend that I know enough about the mathematics with these circuits to be able to teach effectively. I certainly don't want to do that. So, I hope you don't mind. I just wanted to take this opportunity really to share with you that my intent through these videos is not to educate about electrical engineering. I'm trying to build something here with you. I want to go through this journey of designing and building this lighting system. And that's the focus of what we're going to do. So, depending on your, existing knowledge on electronics and electrical engineering, if you have plenty more than me, then please, help me out. Tell me where I'm going wrong, or maybe suggest some ideas on how we can actually do this better. I'm looking forward to hearing from you about how we can do better. But if you're on the other side of the fence and perhaps you're new to electronics or electrical engineering, right? Use this as an opportunity to kind of, we're going on a practical journey, put it that way, right? And so use this as somehow, we can proceed on this practical journey, but I am going to deliberately skip over a lot of the fundamental basics. I want to try to focus on the practical, the practical accomplishments of getting to the point of where we can actually build this. So, if there's something you don't understand, ask away. There's lots of people out there who are more than willing to help out and give you a better understanding about what's going on, myself included. I'll try as much as I can. But yeah, there's tons of content out there. And so as a result, I'm going to keep the mathematics and I'm going to keep the mathematics simple through these set of videos, right? And we're going to focus on the practical engineering to get ourselves towards the point of actually building this. So yeah, I was just doing some thinking over the time I did the last video. I thought, yeah, let me see if I can share this. So yeah, take it for what you will, right? That's just the kind of person I am. I'm a bit more practical rather than theoretical. When it comes to a certain circuit, if I don't understand it, I'll just build it. And through that process, I tend to understand things a little bit better. And that circuit that we showed yesterday, that was a perfect example of that situation, right? Like I looked at that circuit and I wasn't kidding. My head was hurting trying to understand how that feedback mechanism was going through with these transistors. If you haven't seen the video, take a look. Here's the link to it. Just one, or actually right over here. So take a look at the last video, and you'll see what I'm talking about. The circuit was just, my head still hurts thinking about how it's going to work. And so I wanted to move forward from that because I can easily get stuck in this, cycle of not understanding and trying to do the math to figure it out. But because of my inability to excel at mathematics, I'll never win at that. And so I'm much better at just building stuff and seeing how it goes from there. So refresher, right? I mean, let's look at what we did last time. So, okay. I'll get this up on the screen here so we can see it. What we did last time was we looked at this circuit, and this was the original, very simple circuit that we wanted to use to go from taking our LED. Where's my pencil? Here it is. Taking our LED, lightening it up, and using that parachute to slow down our descent, so we're actually able to light that up reliably. But we had a lot of problems with this, right? It really wasn't all that reliable. So then we went to this other circuit which I had modified. I mean, I didn't modify. Of course, I found the link to a site online which modified that circuit to help us understand what was actually happening here to get us to this point where there still is a bit of confusion in my mind how this feedback mechanism works, but I can understand this a heck of a lot better than I could the other one. And there was a few things that first stood out for me, right? This point right here, this parachute resistor is really well controlled. Because of this transistor, I know that this point right here, the voltage right here, is always going to be roughly 0.65 volts, right? I mean, it's not always going to be exactly that. It's going to change, of course, depending on this transistors. Some of them are lower, some of them are higher, depending on which one you actually use. But it's generally going to be fixed. I mean, it'll move a little bit, but for the most part, it'll be fixed. And so if that is fixed, well, that means we have good control over this parachute resistor. So we can actually control the amount of current going through our LED really well with this setup, right? And the other thing we have is we have this current path right here, which is not going to be a current path, which makes it easier for us to understand this. Now, what the voltage here at this point is, I don't know. But like I said on the last video, we're going to build it. We're going to build this circuit to try to figure out what this voltage is. And then we'll have a better idea of how much current is actually going through here and how much current is going to be going through our LED. Let's do a couple of calculations first, right? I want to do a couple of calculations to figure out what we need to size this resistor at. And I'm going to do a couple of power calculations too, so we can figure out if our resistor is capable of doing this. Okay, so just before I jump into the calculations, I also want to put another value up here. And this is going to be our target current that we want to run this at. Because remember, I don't want to use the same old LED that we did last time, that little one that was 20 milliamp. I want to use the big one. Right, I want to use this guy right here because this is going to burn a lot brighter, right? and that's our intent, right? We want to get some nice bright LEDs to illuminate our room. So I want to use this one right here, and so as a result, put that over here. As a result, the current that I want to generate in order to the rated current for this LED is 350 milliamps. Okay, so bear with me while I do some calculations to figure out what this resistor size is going to be in order to meet this current target current that we have here. Okay, here we go. All right, there it is. Right? So I figured out that in order to get 350 milliamps through this current branch over here, or more accurately through this resistor, this parachute resistor needs to be sized at 1.86 ohms. That's a lot smaller than the last resistor we saw, right? 1.86 ohms. But even if we do size it at 1.86 ohms, the power that this resistor needs to dissipate in terms of heat is 228 milliwatts. Now, a lot of resistors are rated for 250 milliwatts. So this is actually underneath that, which means we should be okay. It's going to get warm, but it should be sufficient to be able to handle this kind of power. All right, so that resistor we should be able to acquire and put in. Now, I don't actually have a 1.86 ohm resistor handy on me right now. So what I'm going to do is I'm going to use a different resistor. So this is a resistor that I have available. Let me make sure I got the right one. Yeah, this is it, I think. Okay, so this resistor right here, this is actually a 6.2 ohm resistor. So it's not quite 1.86. It's a lot larger than 1.86, 6.2 ohm. But what that means is that we're going to actually have to run a lot less current than 350 if we're going to choose to use this resistor. But I think we're going to go ahead and do this for another reason. Obviously, one, I don't have such a small resistor. Two, it's definitely going to be safer to run this because the power is going to be a lot less. And the other reason I want to run this is, let me show you what's on the other side of this LED. So these high power LEDs, if you flip this around, you're going to see a metal plate on the other side. And these metal plates are there for a reason. When you run that kind of current through a small device like this, even though these LEDs don't get as hot as those incandescent bulbs, they still generate some heat. There is some waste heat generated out of this LED. And so the reason they have this metal plate on the back is it's designed to be anchored or placed on a heat sink or something metal, large and metal, that can take that excess heat energy away so we don't actually damage it. If we don't put this on something metal, then it'll run for a little while, but eventually that heat is going to be too much for this thing to bear, and it's going to fail, especially if you run it at high current. So to avoid failing or destroying my LED so soon, and also to avoid going to the trouble of anchoring this to a heatsink for now, what I'm going to do is I'm going to run this at lower current. So I want to run it at lower current using this resistor, and that means we're going to be able to do some more testing. We won't burn this LED out anymore. So why don't I do the calculations to see what actual current I'll be running through this using this resistor. Hey, bear with me while I figure that one out. All right, so there's the new numbers. If we use this resistor, which is 6.2 ohms, that means that I'm going to have a current going through this resistor of 105 milliamps. And if this circuit behaves the way I think it does, then most of that 105 milliamps is going to be going through this LED, which means it'll be running at, well, a lot less than a third of its maximum intensity, but still quite a lot higher than the last one we ran. And the last one we ran, remember, was rated for 20 milliamps, but we were running it for like, I think 10 or 11 milliamps. So this is going to be, ideally 10 times brighter than the old LED. And if you want to see that old LED and the intensity that it generated, make sure you look at the last video and you'll be able to see that older 20 milliamp LED running. So now we're going to try to run this one at 105 milliamps. Also, because of the reduced current, the amount of power that this energy or this resistor is going to be dissipating is a lot less. 68 milliwatts, it's probably going to be cool enough to touch using that. So we're going to build the circuit using this resistor, that LED, and we're also going to have a couple of new components here, right? We're going to have to figure out a MOSFET to use, and we're going to have to figure out a transistor to use. All right, so let me go get, you know what? I actually have these ones right here. Let me see if I can bring it up here. So this one, okay, here, I'm gonna do this a little bit different. So I'm gonna put this over here and move this over there. And let me bring my, okay, here we go. I'm dropping stuff as I do this, but that's all right. Okay, so I got my little static pad here to make sure that I don't short these things out, because now we're working with transistors and MOSFETs. These things are sensitive to static electricity. So I just want to make sure I take the precautions, because hey, I mean, look, the chances of actually frying these things with static electricity is really slim, but I've done it before. Okay, and also you can't see this, but I actually have a rug underneath me, so I don't want to take any chances here. So I'm just going to use my static pad. I also got my wrist guard here, or my static wristband here, so make sure that I don't fry any stuff here. Okay, so I got two devices here, and these are the transistor and the oh boy, hold on a second. I can't see which one this is. Okay, I'll figure it out later. I need a bit of a brighter light to understand what this thing is. If I can take a closer look here. Okay, yeah, I got it. This is my transistor. So this one right here, let's put this on the left side. This is my transistor. That's a 2N3 3904, which is actually like, I don't know. I grew up using these in school, so like to me, they're like the world's most common transistor available. It's a very, very common piece. And this is a MOSFET that I had available. I know it looks exactly like the transistor, which is what's causing me a headache right now because I can't tell them apart. But this is a MOSFET here, and if I look at what this one is, it's a BS270. All right, so it's a MOSFET. Again, I'm going to keep them on opposite sides of the static met here, so I keep them separated. But these are the two pieces I'm going to use. So this is the transistor Q1, and this is going to be the MOSFET for Q2. And we're going to have to plug these in a particular way. Let me actually bring up the data sheet here so we can see how to plug this thing in. So the data sheet that I'm going to bring up first, let me there we go. Sorry, just bear with me here while I grab that data sheet. Okay, and this is the, oh, it's not exactly this. Oh, you know what? I can't use this one. Okay, let's look online. I actually don't happen to have the data sheet handy for this, so I'm just going to look online and luckily, it's actually really easy to find these data sheets online. So, oh, look at that. Found it right away. Top one. Let me share the screen so you can see what we're looking at here. There we go. So this is the data sheet for the transistor. This is the one on the left side that we were looking at earlier, right? The Q1. It's a 2N3904. So what's important here for us to know is the thing that how it plugs in. So if you remember the schematic, we had a base, which is going to be the second pin here, and then we had the top pin, which is 1, and then we had the bottom pin, which is 3. So I'm going to make sure we hook this up in the right way, and this diagram kind of tells us which way to hook these things up. So this is going to be very important for us. The other data sheet that I'm also going to share here is this one. So this is the BS270 N-channel enhancement mode field effect transistor. Very big name for a MOSFET that we have. But this one has a similar diagram here that tells us the right way to plug it in. So it shows us the ground, it shows us the drain and the source, and the way that device pins are going to be arranged. So that's going to help us actually plug this thing in. The other thing that I'll do while I have this data sheet up is I'm going to look at this first bullet here. It says, or the first table, which talks about its absolute maximum ratings. This is important. When we start choosing components to put into our circuits, you want to take a look at this data sheet. It's going to help us to understand whether or not we're exceeding any sort of capabilities of these devices. And the one thing that's important for now is looking at this, the drain current. So this is the current that can pass through this transistor safely. And it says that it can continuously pass 400 milliamps through it safely. Now, if you remember, we were going to run 350 milliamps through this to run that one LED. This is plenty. It'll be able to handle that just fine. But we're going to be well below that with the first build. We're going to be building this at 105 milliamps. So this MOSFET will easily be able to handle the kind of current we're going to be pushing through it. So it's important to look at these data sheets as we start using these devices to make sure that they can handle the kind of stresses we're going to be putting on them. Okay. So that's it. I'm going to use these data sheets to help me figure out how to organize or orient these devices in my circuit. So give me a few moments and I'll plug all this in and we can see what's going to happen here. All right, here we go. Okay, you saw my masterful soldering skills at work there. Um, yeah, I can do better. All right, so here we go. I've got everything plugged in, I think, the way it should be for our design. So we have our BS270 MOSFET right over here at the top, and then below that we have our transistor, which is Q1. This is our R2, which is, this is our parachute resistor down here, 6.2 ohm, which is this one over here. And this one at the top here is this 1 kilo ohm resistor. Sorry, you know what? I didn't write down there. This is actually supposed to be 1 kilo ohm resistor based on the design that we found online. Okay, so that's there. That's there. It looks like everything's in place. Let me add 5 volts. And let's see what happens. All right. Oh, of course, my LED's not plugged in. Okay, yeah. The reason I didn't do that is because, okay, so as I mentioned, I think I mentioned in a previous video that LEDs have one way to plug in. They can either go one way or the other. They won't go the other way because if you look at the way the diagram here is, right, it has to go in one direction. It's either top to bottom. If you try to flip this LED around, it won't work. It only allows current to flow one way. And these particular LEDs, these are a bit older. I practically wouldn't use them in any modern design, but they're great for testing. The disadvantage, though, is I can't actually tell which side is the anode and which is the cathode. I don't know. So we're gonna try it and see what happens. So I'm just gonna plug it in. The green wire, or this side of this, is going to go straight to the supply. So that's the top rail over here. And then the other side of this is going to go, to the top of that MOSFET, which is right here. Let's see if this thing lights up. It doesn't light up. Okay, so I guess I got it the wrong way. Let me try the other way. Flip this around. I'm just aiming this so when it does light up, it doesn't shine bright in my eyes. It's really the only reason I'm doing that. Okay, so I'll put this in the top rail, and the second one goes right over here. And oh, still doesn't work. Okay, hold on. Figure out what happened here. Hang on. Okay, so that one works. All right, interesting. So I actually, okay, so here's where I must admit, I have two of these. And so what I did was, in order to kind of show you my soldering capabilities, my fabulous soldering capabilities, I soldered this on the video now so you can see what I was doing. But either I really screwed up my soldering capabilities, or this LED has already been toast, because I pulled in another LED from a test I did previously, and look at this, it works as expected. There we go. All right. So I plugged everything in the way it should have, but it was the LED. Anyways, look at this. It is so much brighter than the other LED that we had, the 20 milliamp. And it's exactly what we'd expect, right? This thing should be drawing roughly 100 milliwatts based on our circuit that we designed here, or exactly 105 milliwatts. And so as a result, it's wonderfully bright. Okay, this is really, really nice. Okay, so one of the things I want to do is let's check our voltages. So let's turn on the scope, and we can see what our regular voltage is here. Okay, so now it's going to be tough for you, of course, to see. Oh, not that one. Here we go. All right, so it's going to be tough for you to see. You know what? Here, I'll put this up on the screen as well, and then you can see all of the different things as we are probing this. So let me pull this. Let me connect my probe. All right, now first thing I'll do is I'll check our supply voltage, make sure that we are actually at 5 volts. And we're actually a little bit low, 4.9. Let me up it just a touch so we can get to, oh, there we go. Bingo, 5.02, close enough. 5 volts coming in our supply. All right, and then what I'll do is I'm going to check, let me get my pencil here. All right, so we got 5 volts coming in our supply over here. What I want to do is I want to check the value of this R. Now I guessed, or I put this in at 0.65, so let's actually see what it is. I'm just going to put the probe in there, and we are at 700 millivolts. It's actually a bit higher than what I expected, but that's 0.7 volts now here. So 0.7 volts. Now what that means is if this is at 0.7 volts, and this isn't exactly at 105 milliamps, but it's going to be close enough. The difference is not going to be huge. Okay, so this is at 0.7. I wonder what this voltage is at. Let's take a look and see what this voltage is at. So that location is right over here on the probe, and it's reading 3.8 volts right here. So we're at 3.8 volts right here, and if we do the mathematics, that voltage drop across this 1 kilo ohm resistor is about 1.2 volts, which means we have 1.2 milliamps going through here. Okay, so this is pretty cool. What this means is that through this branch over here, on the left, through this resistor, we have just over 1 milliamp, and through this branch, through the LED, we have almost 100 milliamps. So 100 times less current going through this side to make sure that this thing is biased. That's pretty good, actually. Given, if you think about the efficiency of this, we're only wasting 1 milliamp to make sure that this feedback mechanism works the way it should. And most of our current, 99 roughly % of our current, is going through our LED to light it up. Hey, that's not bad at all. That's pretty good. All right, so let's check something else here as well. Maybe what I'll do is, remember the last one, we were comparing, when we change the voltage, let's see what happens to our intensity. So I'm just going to put the probe right at here. I'm putting the probe right over here so we can measure the voltage going through R. And I'm going to vary this voltage a little bit here. Let's see what we can do. Okay, so I'm going to pop this voltage up and down. Look at that. That's barely changing. It's 750 millivolts. Nope, not even 750. It's 700. It's staying very close to 7.7 volts. If I drop it down a bit though, it starts to drop down to, oh, there we go. That's where it sunk down. Okay, so at this point, we're not able to get over the wall. Remember earlier we talked about that LED wall? There's not enough energy to get over that wall, which is why it barely enough. So I can see the LED is glowing a little bit, but it's not really achieving its proper glow until we get to zero point 0.6 volts. And then at that point, even if I increase the um, voltage across this resistor stays pretty constant at 0.7. It's not moving. Look at this. I'm at 750 millivolts across this resistor. So it hasn't changed a lot. And take a look at my supply voltage. Look what I'm at now. I'm at 9.4 volts, almost 10 volts here. There we go. I'm at 10 volts supply voltage, and the voltage across our parachute resistor is 750 millivolts. So a very small difference. We went from 0.7 to 0.75 volts across that parachute resistor. So that is far better control than what we were getting earlier. And you can visually see that even if this is easier to see, even if I adjust my supply voltage, as long as I remain over that wall, the intensity of the LED doesn't change. Hey, this is pretty good. This is far better than what we had before, and this is going to allow us to control our system really well. So we've done a couple of things, right? We've been able to remove the dependency of voltage on our circuit. Let me turn off the scope. We don't need the scope anymore. Okay, so I've been able to do a couple of things. We've been able to remove the dependency on our circuit from voltage. So now, as long as we have enough to get over that original wall, we're going to be able to run this at a relatively constant current. That's really good. The other thing that we've been able to do is I've been able to safely run a nice high current through this LED, even with a tiny little parachute resistor, right? And it's not burnt. Let me touch it actually. So we should have 68 millivolts is nothing. 68 milliwatts. You can barely feel it. There's nothing. I'm sure if I touched that onto my lips, perhaps I'd feel something, but just touching with my fingers is nothing. There's nothing to be concerned about at all. We're only burning off a little bit of excess power here. This should be roughly 68 milliwatts. So this is easily able to handle this. And I like this circuit. This is actually a really nice circuit, I think, right? So, but there is something that confuses me here. So if I think about what's happening here, let me move this aside just a little bit. If I think about what's happening here, the voltage at this point right here, we know that this is 6.65. That's the number we have over here. This is a 0.65 voltage level. I use my pencil for this. This is at 0.65, right? Okay, so we know this is at 0.65. We also, oh, you know what? Let me measure it. We didn't measure what the voltage drop across this LED is. Let's do that. I'm going to turn the scope back on. Let's turn the scope back on. Okay, and I'm going to take my scope and I'm going to probe first let's probe at the supply again. Let's make sure we're at 5 volts. And 5.86. Let me adjust this so we can get right back to 5 volts. Bring that down a bit. There we go, 5.02, good enough. Okay, so we're at 5 volts now. And the next thing I'm going to do is I'm going to probe on the other side of that LED, right over here. And let's see what the value of this voltage is. There we are. 2.2 volts. That's actually a lot like the other one, isn't it? 2.2 volts. That means the voltage drop across this resistor is 2.8 volts, just like scenario 1 from the previous example. Hey, that's pretty cool. Okay, so what does this mean? This means at this point right here, on the top end of this MOSFET, we're at 2.2 volts. And at the bottom end of this MOSFET, we're at 0.65 or 0.7 volts. So that means there's a voltage drop across this MOSFET. We have a voltage drop across the MOSFET, and we know we have current flowing through this MOSFET. That means there must be power dissipating from this MOSFET. This thing might be getting warm. Okay, let's see if I can put my finger on it. I don't feel anything. So it's probably not getting warm enough for me to feel, but there's got to be power being dissipated from this MOSFET. That's the only explanation. If there's a voltage drop across it, it's got to be using that energy somehow. The only way the MOSFET can use energy is by pushing it out through heat, because there's got to be somewhere for the energy to go. Well, let's do a quick calculation. Let's figure out what that power dissipation is on that MOSFET. I think it's probably going to be important for us. Let's figure that out. Okay, bear with me. I'll move this aside and do a quick calculation here. All right, there you have it. So the power dissipation out of this MOSFET, based on these calculations, should be 160 milliwatts. That's how much this thing is dissipating right now. Let me take a quick look at the data sheet for this MOSFET. Here, I'll bring it up on the screen here. There we go. Right one? Yeah, that's the MOSFET we're looking at. Let's take a look at the power dissipation capabilities. Maximum power dissipation, 625. Well, we're well below that. This is fantastic. We're at 160 milliwatts. This thing can handle 625 milliwatts. I think we're well in the safe zone. All right, well, isn't that interesting to know? So that means that with this circuit that we have right now, we are safely running everything within its, I guess, tolerated, within its tolerances. That's the word I'm looking for. So we can safely run this within its tolerances, and it's running, well, efficiently, because we have very little wastage current going through the first branch. We have a low dependency on voltage. We have a good, solid, current-controlled source. Huh, well, that's pretty good. So I think the next thing that we want to be able to do, of course, since we're doing illumination, we want to be able to dim these lights. And so we know that this resistor right here, this is the parachute resistor. So this resistor right here, this is this one right here. All right. And we know that if I control, or if I change this, then I'll be able to get a dimmer light. Let me, for fun here, I'm going to add another resistor in. Let's see, let's change this. Right now it's a 6.2. I'm going to change this to the 200 ohm resistor I had earlier. So if I change it to 200 ohm, from going from 6.2 to 200, that's a much bigger parachute. And we expect this thing to dim quite considerably if I do that. So let's do this and see what happens here. So I'm going to plug this in here. There we go. That is a lot dimmer. That is quite a lot dimmer than the 6.2, and that's exactly what I would expect for this. And if I look at my scope, it actually doesn't even register how much milliamps this thing is pulling, so it's definitely going to be a lot less. But hey, I think we're onto something here, right? If we're able to adjust that resistor, we should be able to do some pretty fancy dimming. I just stuck that 6.2 back in. I can take it out and put it back in. All right. I think we're onto something. This is going to allow us to dim our light just by controlling this one parachute resistor. I think we're onto a good start here. Okay, that's fantastic. So I think, like I said, I think we're onto a good start. One of the things that I'd like to talk about, actually, I'm going to save this for the next video, right? Because we went pretty long today. What I want to do is I'm going to save it for the next video. There is one other circuit that I did find online that I want to be able to share with you. That is a very different way to dim LEDs, different than what I just showed right now. And I think it's going to be important to talk about it because I found that it's pretty common out there. And spoiler alert, I don't like it. And there's some reasons I don't like it. So we'll get into that onto the next video, or in the next video, as to why I don't like some of the more common ways to do LED dimming. But until then, yeah, enjoy yourself. I hope you enjoyed today's video. Again, if you want to subscribe to the channel, it'll be fantastic. Once I get the next video up, you'll get your notification so you can watch us get into the dimming methodology that I don't like. See you then.